From the ether of space, our planet appears as a seamless blue marble, a world defined by its vast and restless oceans. Yet, nestled within the folds of its great land masses are other waters, countless mirrors to the sky that have nurtured life and shaped civilizations since time immemorial. These are the Great Lakes of the world, bodies of water so immense they create their own weather, so deep they could swallow mountains, and so ancient they hold the secrets of planetary history in their silent depths. If you enjoy stories about the natural wonders of our world, be sure to subscribe so you are notified of future stories. A lake, in its simplest form, is a body of water localized in a basin, surrounded by land and separate from the ocean. But this simple definition belies a staggering diversity. They are born from cataclysmic forces, the violent collapse of volcanoes, the slow, grinding retreat of colossal glaciers, and the subtle, inexorable shifting of the Earth's crust. Most are filled with fresh water, accounting for almost all of the liquid fresh water on the planet's surface, a precious resource that dictates the flow of life around it. They range from ephemeral pools that exist for a single season to ancient rift valleys filled with water that has remained undisturbed for millions of years. Together, these bodies of water are not merely passive features on a map. They are dynamic, living systems, the heart of intricate ecosystems and the cradle of human history, each with a unique and compelling story waiting to be told. Our journey begins not with a freshwater lake, but with a magnificent paradox. A body of water so vast, it challenges our very definition of the word. We travel to the heart of Eurasia, to a place where the continents of Europe and Asia collide, to witness the Caspian Sea. It is, by every measure, the largest lake on Earth, a sprawling inland water body that dwarfs all others. Yet its name carries the legacy of a sea, and for good reason. It is salty, vast, and in its deepest basins, it possesses an oceanic crust, a ghost of a true ocean floor. This ambiguity is not a mere quirk of cartography. It is the living legacy of a profound geological history, a story of continental collisions, shrinking oceans, and a trapped remnant of a long, lost world. To understand the Caspian, we must travel back in time, far beyond the reach of human history, to an era when the world map was profoundly different. Some 55 million years ago, in the early Cenozoic era, a vast, shallow ocean called the Tethys connected the Atlantic and Pacific, separating the ancient supercontinents of Laurasia and Gondwana. As the African, Arabian, and Indian plates drifted relentlessly northward, they began to squeeze the Tethys, buckling the Earth's crust and thrusting up the great mountain ranges that stretch from the Alps to the Himalayas. This colossal geological upheaval, known as the Alpine orogeny, did not happen overnight, but over tens of millions of years. A large portion of the Tethys was cut off from the global ocean, forming an immense inland sea that geologists call the Paratethys. For millions of years, the Paratethys Sea ebbed and flowed, at times stretching from the region of modern-day Austria all the way into Central Asia. It was a world of its own, with a unique ecosystem of whales, dolphins, and sharks adapted to its brackish waters. But its connection to the world's oceans was tenuous. As the mountains continued to rise and global sea levels fell, the Paratethys became increasingly isolated. It began a long, slow process of shrinking and fragmenting, its waters evaporating under the Eurasian sun, leaving behind smaller bodies of water like the Black Sea, the Aral Sea, and the greatest of them all, the Caspian. Today, the Caspian Sea is the final, magnificent chapter in the story of the Paratethys. It is a landlocked giant, covering an astonishing surface area of 371,000 square kilometers, or about 143,000 square miles. This is larger than the nation of Germany and represents more than 40% of the total water of all the world's lakes combined. Its volume is equally staggering, holding 78,200 cubic kilometers, or about 18,800 cubic miles of water, roughly 3.5 times the water of all 5 of North America's Great Lakes. Put together, 5 nations share its lengthy coastline of nearly 7,000 kilometers, which is approximately 4,350 miles. Russia to the northwest, Kazakhstan to the northeast, Turkmenistan to the southeast, Iran to the south, and Azerbaijan to the southwest. The character of the lake changes dramatically as one travels from north to south, a result of its division into 3 distinct basins. The northern Caspian is incredibly shallow, averaging a mere 5 to 6 meters, or 16 to 20 feet deep. In winter, its frigid, less saline waters often freeze over. The middle Caspian is deeper, a transitional zone that gives way to the Great Southern Caspian Basin, where the lake floor plunges to a maximum depth of 1,025 meters, or 3,360 feet, placing its bottom far below sea level. This immense depth is a direct consequence of its ancient oceanic heritage. The lifeblood of this great lake flows from the north. Over 130 rivers drain into its basin, but the most significant by far is the Volga, Europe's longest river. The Volga, along with the Ural River, pours in from the vast Russian plains, delivering nearly 90% of the Caspian's total freshwater inflow. This constant influx of fresh water is crucial, as the Caspian has no outlet to the ocean. It is an endorheic basin, a closed system where water can only escape through evaporation. This process is the key to its salinity. As water evaporates from the lake's surface, the salts and minerals carried in by the rivers are left behind, gradually concentrating over millennia. The result is brackish water, with an average salinity of about 12 parts per thousand, roughly 1/3 the saltiness of the world's oceans. This salinity is not uniform. Near the Volga Delta in the north, the water is almost fresh, while in the isolated, shallow lagoon of Kara-Bogaz Gol in Turkmenistan, evaporation is so extreme that the water is hypersaline, and vast salt pans crust its shores. This unique environment, born from a blend of freshwater and saltwater characteristics, has given rise to a singular ecosystem. The Caspian is an ark of life, home to hundreds of species found nowhere else on Earth. Its most famous resident is the Caspian seal, the only aquatic mammal to inhabit the lake. These seals are a relic population, their ancestors having been trapped in the Paratethys millions of years ago when it was still connected to the Arctic Ocean. They have since adapted perfectly to this landlocked world, giving birth to their pups on the floating ice sheets of the northern Caspian each winter. But the true treasures of the Caspian are its legendary sturgeon. 6 species of these ancient, armored fish swim in its waters, including the beluga sturgeon, the largest freshwater fish in the world, capable of growing to over 7 meters, or 24 feet, in length and living for more than a century. For generations, these living fossils have been the source of the world's most prized caviar, a black gold that has been as coveted as the crude oil that lies beneath the lake bed. The sturgeon, however, represent the fragility of this unique world. Overfishing, driven by the astronomical price of caviar, and the damming of rivers, like the Volga, which blocks their ancient spawning routes, have driven these magnificent creatures to the brink of extinction. Beneath the water and the ancient sediments lies another kind of treasure, one that has reshaped the geopolitics of the 21st century. The Caspian Basin holds one of the world's largest reserves of oil and natural gas. The discovery and exploitation of these vast hydrocarbon fields since the late 20th century have brought immense wealth to the region, leading to the construction of massive offshore platforms and pipelines that crisscross the landscape. This black gold rush has also intensified the age-old debate: is the Caspian a sea or a lake? The question is far from academic. If it is legally defined as a sea, international maritime law applies, and the 5 bordering nations would divide its resources based on median lines extending from their coasts. But if it is a lake, the countries must collectively agree on how to divide the entire body of water and its valuable floor. For decades after the collapse of the Soviet Union, this legal limbo created tension and uncertainty. Finally, in 2018, the 5 littoral states signed the Convention on the Legal Status of the Caspian Sea, a historic agreement that treats it with a special legal status, neither fully sea nor fully lake, a diplomatic solution that mirrors its unique natural identity. But the pressures on this fragile giant continue to mount. Pollution from the oil industry and industrial and agricultural runoff from the Volga and other rivers degrade its water quality. Invasive species, accidentally introduced in the ballast water of ships, have disrupted the food web. And the lake's water level is in constant flux, a natural cycle now dangerously amplified by climate change and the upstream diversion of river water for agriculture, threatening a catastrophic fall in the coming decades. The Caspian Sea, therefore, is far more than just the world's largest lake. It is a geological echo of a vanished ocean, a biological museum of unique life forms, a battleground for resources, and a stark warning of the environmental consequences of human activity. It remains a world unto itself, a salty, sprawling, and singular marvel trapped between two continents. Leaving the ancient, salty basin of the Caspian behind, our journey now takes us across the Atlantic to a different kind of immensity, a world of sweet water so vast it forms a liquid heartland for an entire continent. We arrive in North America, home to the Great Lakes, a chain of 5 interconnected freshwater seas that together constitute the largest such system on Earth. They hold a staggering 21% of the world's surface freshwater, a treasure of more than 22,600 cubic kilometers, or 5,400 cubic miles. This is not a single body of water, but a family of giants: Superior, Michigan, Huron, Erie, and Ontario, that flow one into the next, a grand aquatic staircase descending from the continent's interior to the Atlantic Ocean via the St. Lawrence River. Their story is not one of trapped oceans or shifting tectonic plates, but a dramatic tale of ice and rock, a saga written across the land by the unimaginable power of glaciers. To understand their origin, we must rewind the clock to the Pleistocene epoch, the Great Ice Age that began over 2.5 million years ago. Before the ice came, this region was a landscape of ancient river valleys carved into the bedrock of the Canadian Shield. These valleys followed lines of weakness, tracing paths through softer, sedimentary rocks like shale and limestone that had been laid down in primordial seas hundreds of millions of years earlier. Then the climate cooled, and the snows of winter began to outlast the summer melt. Year after year, century after century, the snow compressed into colossal sheets of ice, forming the Laurentide ice sheet. This was a glacier of continental proportions, at times burying North America from the Arctic to as far south as modern-day Ohio under a crushing weight of ice that was in some places over 3 kilometers, or nearly 2 miles, thick. This was no static mass. It was a slow-moving river of ice, a planetary-scale bulldozer. As it advanced southward, it acted as a colossal abrasive, scouring the landscape with unimaginable force. The harder, more ancient granites of the Canadian Shield were scraped clean, but the softer rocks of the pre-existing river valleys were gouged out. their channels deepened and widened by the relentless grinding of the ice and the rock debris frozen within its base. Over thousands of years, the glaciers advanced and retreated several times with the planet's fluctuating climate, each passage acting like an icy scalpel, carving the basins of the future Great Lakes ever deeper. Around 14,000 years ago, the Earth entered a warming phase, and the Laurentide ice sheet began its final, prolonged retreat. As the ice melted, it released biblical volumes of water, which became trapped in the immense depressions it had just finished carving. The land itself, relieved of the crushing weight of the ice, began to slowly rebound, a process of isostatic adjustment that continues to this day, subtly tilting the lake basins and altering their shorelines over geological time. The result of this glacial cataclysm is the magnificent system we see today. A chain of lakes so large they are visible from the moon. Water from the wild, remote basin of Lake Superior, the highest and most westerly of the group, flows into Lake Huron. Lake Michigan, the only one of the 5 located entirely within the United States, joins Huron through the wide straits of Mackinac, making them hydrologically a single lake. From Huron, the water flows south into the St. Clair River, through the small Lake St. Clair, and down the Detroit River into Lake Erie. Erie, the shallowest and warmest of the Great Lakes, then spills over a massive escarpment in a thundering cascade of mist and power, creating Niagara Falls, one of the world's most spectacular waterfalls. Below the falls, the water enters Lake Ontario, the smallest by surface area, but still incredibly deep, before finally exiting through the St. Lawrence River on its long journey to the Atlantic. Our focus, however, must be on the headwaters of this system, the majestic and untamed giant known as Lake Superior. The early French explorers and voyageurs who navigated its waters in birch bark canoes aptly named it Le Lac Supérieur, meaning the upper lake. But its original name, given by the Anishinaabe people who have lived on its shores for centuries, is Gichigami, or Great Water, a name that more accurately captures its profound scale and power. By surface area, Lake Superior is the largest freshwater lake on the entire planet. It stretches across 82,100 square kilometers, or 31,700 square miles, an expanse large enough to contain the states of Massachusetts, Connecticut, Rhode Island, and Vermont combined. It is a profoundly deep and voluminous lake, holding 12,100 cubic kilometers, or 2,900 cubic miles of cold, astonishingly clear water, more than all the other 4 Great Lakes combined. At its deepest point, the lake floor plunges to 406 meters, or 1,333 feet, well below sea level. The water that enters Lake Superior remains there for an average of 191 years before it flows out into Lake Huron, a testament to its immense volume and slow, methodical nature. Its shores are rugged and sparsely populated, dominated by the ancient glacier-scoured rock of the Canadian Shield and vast boreal forests. This untamed wilderness stands in stark contrast to the heavily industrialized and populated shorelines of the lower lakes like Erie and Ontario. For centuries, this great water was the centerpiece of Anishinaabe life and spirituality. Then, in the 17th century, came the French, seeking not land, but furs. The voyageurs plied these waters, establishing a trading network that connected the continent's interior to Europe. But the true transformation of the region began in the mid-19th century, with the discovery of vast deposits of iron ore and copper in the lands surrounding the lake. This mineral wealth, combined with the seemingly endless forests of white pine, turned Lake Superior into a crucial artery for the Industrial Revolution sweeping North America. A new kind of vessel appeared on its waters, the lake freighter, or laker, long, narrow ships designed specifically to carry immense cargoes of iron ore, coal, and grain. These steel behemoths, some stretching over 300 meters or 1,000 feet, became the workhorses of the lakes. To make this industrial machine possible, human ingenuity had to overcome the natural barriers of the landscape. The rapids on the St. Mary's River, which connects Superior to Huron, were bypassed by the construction of the Soo Locks, an engineering marvel that allows ships to be lifted and lowered the 7 meters, or 21 feet, of elevation difference between the two lakes. These locks became the linchpin of a continental shipping system, the steel arteries that carried the raw materials from the mines and forests of the north to the steel mills and factories of cities like Detroit, Cleveland, and Chicago. This industrialization, however, came at a steep ecological price. Overfishing depleted stocks of native lake trout and whitefish, runoff from mines, and waste from pulp and paper mills polluted the pristine waters. But the most devastating blow came from an invader that used the man-made shipping canals to enter the upper lakes, the sea lamprey. This parasitic, eel-like fish latched onto native fish and drained them of their bodily fluids, decimating the lake trout population and throwing the entire ecosystem out of balance. The crisis spurred an unprecedented binational effort between the United States and Canada, leading to the Great Lakes Water Quality Agreement of 1972. Decades of work to control the sea, lamprey population, clean up polluted hotspots, and regulate industrial discharge have brought the lake back from the brink. Lake Superior today is a study in contrasts. It remains a wild and beautiful place, a paddler's paradise of cliffs, beaches, and pristine islands. Yet it is also a working waterway, a vital economic engine where massive freighters still glide silently across the cold, clear water, carrying the lifeblood of industry. It is a powerful reminder that even the greatest of waters are not immune to human influence, and that their preservation requires constant vigilance and stewardship. From the ice-scoured heartland of North America, we now traverse the globe, flying eastward over continents and oceans to the vast, wild expanse of Siberia. Here, in the remote and rugged landscape south of the Siberian plains, lies a sliver of brilliant blue, a silver crescent carved into the Earth's crust. This is Lake Baikal, a name that resonates with superlatives. It is not a lake born of ice, but of fire and force, a place where the very continent is tearing itself apart. Known to the local Buryat people as the Sacred Sea, and to scientists as the Galapagos of Russia, Baikal is, by any measure, a world wonder. It is the oldest, the deepest, and by volume, the largest freshwater lake on the planet. A living laboratory of evolution that holds secrets stretching back millions of years. Its story begins not with the grinding of glaciers, but with the violent and inexorable movement of tectonic plates. Baikal lies within the Baikal Rift Zone, a continental rift where the Amurian plate is slowly pulling away from the Eurasian plate at a rate of about 4 millimeters, or roughly 1/6 of an inch, per year. This may seem infinitesimally slow, but over geological time, the consequences are monumental. For the last 25 to 30 million years, this relentless stretching has caused the Earth's crust to thin and drop down between massive fault lines, creating a long, deep, and ever-widening trough. This makes Baikal an infant ocean, a place where, if the process continues for millions of more years, Asia will eventually be split apart and a new sea will form. This immense age sets it apart from almost all other lakes on Earth. While the Great Lakes of North America are geological newborns, formed a mere 10,000 years ago, Baikal is an ancient patriarch, a survivor that has witnessed epochs of climate change, the rise and fall of countless species, and the dawn of humanity itself. This profound age is matched only by its astonishing depth. The lake floor plunges to a staggering 1,642 meters, or 5,387 feet, making it the deepest lake in the world by a significant margin. Its bottom lies more than 1,200 meters, or nearly 4,000 feet, below sea level. A chasm so deep that if the world's tallest buildings were placed on its floor, their spires would still be submerged hundreds of meters beneath the surface. This incredible depth, combined with its respectable surface area of 31,722 square kilometers, or 1,248 square miles, gives it an unparalleled volume. Baikal holds 23,615 cubic kilometers, or 5,665 cubic miles of water. This is a volume so immense that it accounts for approximately 1/5 of all the planet's unfrozen fresh surface water, more than all 5 of the North American Great Lakes combined. It is said that if all other sources of fresh water on Earth were to vanish, Lake Baikal alone could supply the entire human population with drinking water for 40 years. The water itself is as legendary as the lake's dimensions. Baikal is renowned for its astonishing clarity, a purity that is almost spiritual. In the summer, it is possible to see objects at depths of up to 40 meters or 130 feet, as if peering through flawless glass. This extraordinary transparency is the result of several factors. The water that flows into the lake from its surrounding mountain rivers is low in dissolved minerals, and the lake's watershed is relatively small and undeveloped, limiting pollution. But the true secret to Baikal's clarity is a tiny, tireless army of crustaceans. The lake is teeming with a species of copepod shrimp called Episcura baikalensis, an organism found nowhere else on Earth. These minuscule creatures, barely a millimeter long, are the lake's janitors, constantly filtering the water as they feed on bacteria and algae. It is estimated that this crustacean army filters the entire top layer of the lake several times a year, performing a purification service of incredible scale. In winter, Baikal transforms into a different kind of marvel. For nearly 5 months, this vast lake is sealed beneath a sheet of ice that can grow to be 2 meters or over 6 feet thick, strong enough to support trucks and even a seasonal ice highway, the Trans-Baikal Ice Road. The extreme cold, with air temperatures plunging to minus 40 degrees Celsius, which is also minus 40 degrees Fahrenheit, causes the ice sheet to crack and heave. The resulting thermal expansion creates immense shards and hummocks of ice pushed up into miniature mountain ranges on the frozen surface. The ice itself, due to its purity and slow freezing process, is remarkably transparent, often a mesmerizing turquoise blue, offering a window into the dark, silent world below. It is this combination of extreme age, profound depth, and geographic isolation that has made Lake Baikal an unparalleled evolutionary crucible. Over half of the more than 2,500 species of plants and animals found in the lake are endemic, meaning they exist nowhere else on the planet. This extraordinary biodiversity has earned Baikal its Galapagos of Russia moniker. The undisputed icon of the unique ecosystem is the Baikal seal, or Nerpa. It is the world's only exclusively freshwater seal, a biological enigma whose ancestors somehow migrated thousands of kilometers inland from the Arctic Ocean. The leading theory suggests they traveled up a vast river system during a previous ice age when sea levels were higher, eventually becoming trapped in Baikal as the landscape changed. They have since adapted perfectly to this freshwater world, raising their pups in snow dens on the winter ice and diving to astonishing depths in search of fish. Equally strange is the Golomianka, or Baikal oil fish. This ghostly, translucent creature is a marvel of adaptation to the crushing pressures of the deep lake Its body is composed of 35% fat, and it lacks a swim bladder, allowing it to range freely from the depths to the surface. It is viviparous, giving birth to live young, a rarity in cold water fish. The Golomianca is so oily that if left in the sun, its body melts away, leaving behind only its skeleton and a pool of clear fat. This high fat content makes it the primary food source for the Nerpa seals. The lake is also home to the famous Baikal omul, a species of whitefish in the salmon family that is a staple for the local population and a culinary delicacy. For centuries, Baikal has been a place of deep spiritual significance for the Buryat people who live along its shores, a place of powerful shamans and sacred sites, particularly on the vast Olkhon Island, the lake's largest. In the modern era, its scientific significance is paramount. The lake's floor is covered in a layer of sediment that is over 7 kilometers, or more than 4 miles, deep. This sediment, undisturbed for millions of years, contains one of the most detailed continuous climate records on the planet, allowing scientists to look back into the Earth's distant past. The pure, deep water has also made it the perfect site for the Baikal Deep Underwater Neutrino Telescope, a remarkable instrument that uses the lake itself as a detector to search for these elusive subatomic particles from space. Yet even this remote and mighty lake is not immune to threats. The legacy of pollution from a Soviet-era pulp and paper mill, though now closed, lingers on its southern shore. Agricultural and industrial runoff from the Selenga River, its main tributary, introduces nutrients that can cause algal blooms. Poaching, overfishing of the omul, and the pressures of a growing tourism industry all pose challenges. But perhaps the greatest threat is climate change, which is warming the lake's surface waters and reducing the duration of its vital ice cover, with unknown consequences for its unique, cold-adapted ecosystem. Lake Baikal is more than a body of water. It is a living monument to geological time, an irreplaceable natural heritage that continues to challenge our understanding of life on Earth. Our global odyssey now carries us southward, to a continent cleaved by a magnificent geological scar. We arrive in Africa, in the Great Rift Valley, a place where the continental crust is stretching and splitting, birthing a new ocean in the slow, inexorable march of geological time. This is the same titanic force that carved the basin for Lake Baikal. But here in Africa, the scale is grander, the system more complex. The rift stretches for thousands of kilometers, a great wound in the earth that has given rise to a spectacular chain of lakes, known collectively as the African Great Lakes. These are not just bodies of water. They are cradles of life, cauldrons of evolution, and the liquid heart of the continent. The rift system is divided into 2 main branches. The western, or Albertine Rift, is a classic rift valley, a deep, dramatic trough lined with volcanoes and steep escarpments, home to a series of long, narrow, and incredibly deep lakes. The eastern, or Gregory Rift, is a shallower valley marked by a chain of smaller, more alkaline lakes. Between these two arms lies a vast, high plateau, and it is here, in a broad, shallow depression, that we find the largest of them all, a veritable inland ocean. This is Lake Victoria, known in local languages as Nalubaale or Nyanza. By surface area, it is the largest lake in Africa and the largest tropical lake in the world, a colossal expanse of 68,800 square kilometers, or 26,600 square miles. It is so vast that it feels less like a lake and more like a sea, its distant shores often lost beyond the horizon. 3 nations, Uganda, Kenya, and Tanzania, share its coastline, and its waters support one of the densest rural populations on the planet, with tens of millions of people relying on its bounty. Unlike its deep, narrow cousins in the Western Rift, Lake Victoria is a geological anomaly. It is not a true rift lake, but a basin lake formed in the shallow depression created by the gentle upwarping of the land on either side. As a result, it is remarkably shallow for its size, with an average depth of only 40 meters, or 131 feet, and a maximum depth of just 84 meters, or 276 feet. This shallowness, combined with its immense surface area, makes it incredibly sensitive to changes in rainfall and climate. Geologically speaking, it is also very young, having formed only 400,000 years ago, and evidence suggests it has dried up completely several times in its history, most recently around 17,000 years ago. Yet this young lake became the setting for one of the most astonishing and ultimately tragic stories in modern ecology. For millennia, Lake Victoria was home to an incredible diversity of life, most notably a flock of over 500 species of cichlid fish, small, brightly colored creatures that had evolved from a common ancestor to fill every conceivable niche in the lake's ecosystem. This was a spectacular example of adaptive radiation. Then, in the mid-20th century, a fateful decision was made. In an attempt to boost the local fishing industry, British colonial authorities introduced a large, predatory fish not native to the lake, the Nile perch. For several years, the perch remained inconspicuous, but by the late 1970s and early 1980s, its population exploded with catastrophic consequences. The Nile perch, growing to lengths of 2 meters or over 6 feet, and weighing over 200 kilograms or 440 pounds, was a voracious predator in a lake with no natural defenses against it. It systematically devoured the native cichlids, driving an estimated 200 species to extinction in one of the most devastating mass extinctions of vertebrates in modern history. The ecological cascade was immense. The disappearance of the algae-eating cichlids led to a surge in algal blooms, which, upon decaying, depleted the oxygen in the water, creating dead zones. Yet, the story is a paradox. The Nile perch fishery became a multi-billion-dollar industry, exporting fillets to Europe and beyond, creating wealth and jobs even as it destroyed the lake's natural heritage. Today, Lake Victoria is a profoundly altered ecosystem, a stark and enduring lesson in the unpredictable consequences of introducing a foreign species into a balanced environment. From Victoria, we travel westward, descending into the dramatic chasm of the Albertine Rift to find a lake of a completely different character. This is Lake Tanganyika, a long, ribbon-like body of water that is the perfect embodiment of a Rift Valley lake. It is the world's longest freshwater lake, stretching for 673 kilometers, or 418 miles, from north to south. It is also the world's second oldest and second deepest lake, after Baikal, plunging to a depth of 1,470 meters, or 1,820 feet. Its immense volume makes it the second largest freshwater lake on the planet by that measure. Shared by 4 countries, Tanzania, the Democratic Republic of the Congo, Burundi, and Zambia, it is a world of breathtaking beauty, its clear waters flanked by the towering walls of the Rift Valley. Like Baikal, its great age and isolation have made it a hotbed of evolution. It is home to hundreds of endemic species, from brilliantly colored cichlids, which here have had millions of years to evolve, resulting in more complex and diverse lineages than Victoria's, to bizarre snail-shell-dwelling fish and fearsome wolf-like predators. Tanganyika is so deep that the lower layers of water never mix with the upper layers, a condition known as meromictic. This means the water below about 200 meters, or 650 feet, is anoxic, completely devoid of oxygen, and is essentially fossil water. Life in the lake is confined to this upper, oxygenated layer, a thin skin of biodiversity stretched over a vast, lifeless abyss. Our final stop in this African odyssey takes us further south along the rift to Lake Malawi, also known as Lake Nyasa. The third largest lake in Africa, it is another magnificent Rift Valley lake, renowned for its warm, clear, aquamarine waters that are more reminiscent of the Caribbean than a continental interior. But its true fame lies beneath the surface. If Lake Victoria is a story of ecological loss, and Tanganyika a story of ancient depth, Lake Malawi is the world's greatest showcase of evolution in action. It is home to more species of fish than any other lake on Earth, with estimates ranging from 700 to over 1,000 species of cichlids alone. The vast majority of these are endemic, found nowhere else. This is the ultimate example of explosive speciation. Scientists believe that almost all of these species evolved within the lake from a single ancestral species in a remarkably short period of geological time. They have adapted to fill every possible food source and habitat. There are cichlids that scrape algae from rocks, cyclids with powerful jaws that crush snails, and cichlids that have developed highly specialized, often bizarre, feeding strategies, including some that prey exclusively on the scales of other fish, or even, in one notorious case, the eyes. The vibrant, multicolored cichlids, known locally as zambuna, create a dazzling, ever-shifting kaleidoscope of life along the rocky shorelines, turning the lake into a natural aquarium of unparalleled diversity. The African Great Lakes, therefore, are a realm of extremes. They are a testament to the planet's immense geological power, a living theater of evolutionary creation, and a vital resource for millions of people. But they are also fragile worlds, caught in a delicate balance between natural splendor and the ever-growing pressures of human population and development. Their future as uncertain as the shifting continent beneath them. From the fractured crust of Africa, our narrative now arcs across the Atlantic, rising to meet the formidable spine of a different continent. We arrive in South America, a land dominated by the Andes, the longest continental mountain range in the world. This is not a landscape being torn asunder, but one being violently compressed, crumpled, and lifted skyward by the titanic force of the Nazca Oceanic Plate grinding its way beneath the South American continental plate. For millions of years, this collision has thrust rock and earth upward, creating a towering wall of snow-capped peaks and smoldering volcanoes. And it is here, nestled between these colossal mountain chains in a vast, high-altitude plateau, that we find a lake of impossible color and profound legend. High in the Altiplano, where the air is thin and the sun bites with an unfiltered intensity, lies Lake Titicaca, a sapphire set in the arid, wind-swept grasslands. It is a world away from the tropical warmth of Africa's Great Lakes. This is a realm of cold, crystal-clear water held 3,812 meters, or 12,507 feet, above the distant sea. This staggering elevation makes it the highest navigable lake in the world, a place where large commercial vessels ply waters that are closer to the stratosphere than to the ocean floor. By both volume and surface area, it is the largest lake on the South American continent. It covers an area of approximately 8,372 square kilometers, or 3,232 square miles, and plunges to a maximum depth of 281 meters, or 922 feet. The existence of such a massive body of water in this high, dry landscape is a legacy of a wetter past and the unique geology of the Andes. The lake occupies a tectonic basin, a depression formed not by a single rift, but by a complex series of faults that pulled the ground apart between two parallel mountain ranges. Millions of years ago, this entire basin was filled by a vast inland sea known as Lake Bolivian, of which Titicaca is the last great remnant. It is a through-flow lake, fed by rainfall and the meltwater from glaciers perched on the surrounding peaks, which flows into the lake via more than 25 rivers. Its only outlet is the Desaguadero River, which flows south to nourish the much smaller Lake Pupo, a saline lake that often evaporates completely during dry periods. But Titicaca's significance extends far beyond its physical dimensions. This is sacred water, the cradle of Andean civilization. Long before the rise of the Inca, the sophisticated Tiwanaku culture flourished on its southern shores, building a ceremonial center of immense stone monuments. For the Inca themselves, who came later, Lake Titicaca was the very center of their cosmos, the place where the world began. According to their creation myth, the great god Viracocha emerged from the lake's depths to create the sun, the moon, and the stars. It was from a rock on the Isla del Sol, the island of the sun, that he commanded the first humans to walk the earth, and from these waters that the founding couple of the Inca dynasty, Manco Capac and Mama Ocolo, began their journey to establish the city of Cusco. This deep cultural connection to the lake is perhaps best embodied by the remarkable lives of the Uros people. For centuries, they have lived not on the shores, but on the lake itself, inhabiting remarkable floating islands woven from the native totara reeds that grow in the shallow waters. These are not static rafts, but living, breathing platforms. The base is made from large blocks of reed roots, and layers of cut reeds are continuously added to the top as the bottom layers rot away. On these buoyant islands, the Uros build their reed houses, raise their families, and ply the waters in elegant reed boats, living in a symbiotic relationship with the lake that provides them with food, shelter, and their very foundation. The unique high-altitude environment has also fostered a distinct biological community. The cold, oxygen-rich water is home to the critically endangered Titicaca water frog, a bizarre, entirely aquatic amphibian that breathes through its large, saggy folds of skin. The lake is also the only home of the Titicaca grebe, a flightless bird that has lost the need to fly in this vast, isolated aquatic world. Today, however, this sacred lake faces modern pressures: pollution from burgeoning cities along its shores, the introduction of non-native species like rainbow trout, which prey on native fish, and the looming threat of climate change, which shrinks the Andean glaciers that feed the lake, all cast a shadow over its future. From the thin air of the Andes, we now descend to the humid, tropical coast of the Caribbean, to Venezuela, to encounter a body of water that has long held the title of South America's largest lake, yet whose very identity is a matter of debate. This is Lake Maracaibo. In terms of sheer surface area, it is immense, covering over 13,200 square kilometers, or 5,100 square miles. It is a vast, pear-shaped basin that receives fresh water from a multitude of rivers, most notably the Catatumbo River, which flows from the Andes. But unlike Titicaca, Maracaibo is not landlocked. It is connected to the Gulf of Venezuela, and thus the Caribbean Sea, by a narrow strait just 55 kilometers, or 34 miles, long. This connection to the ocean transforms its character. The northern part of the lake is brackish, its salinity rising and falling with the tides, while the southern part remains largely fresh. Geologically, its basin is one of the oldest on Earth, a contemporary of Baikal, formed some 36 million years ago. For millennia, it existed as a true freshwater lake. However, rising sea levels following the last ice age breached the barrier to the north, creating the connection to the sea we see today. Because of this direct link to the ocean, many geographers no longer classify it as a lake at all, but as a large tidal bay or coastal lagoon. This geological ambiguity, however, has not diminished its immense economic importance. In the early 20th century, one of the world's largest oil reserves was discovered beneath the lake bed. For decades, Lake Maracaibo was the heart of Venezuela's economy, a sprawling industrial landscape where a forest of thousands of oil derricks rose from the water's surface, tirelessly pumping black gold. This has left a toxic legacy of pollution, with frequent oil spills and the constant leakage of contaminants turning large parts of the lake into an environmental disaster zone. Yet amid this industrial landscape, Lake Maracaibo holds one of the most spectacular and persistent meteorological phenomena on the planet: the Catatumbo lightning. Here, at the mouth of the Catatumbo River, thunderstorms occur on as many as 300 nights a year for up to 10 hours at a time, producing tens of thousands of lightning strikes. It is a silent, mesmerizing light show, with bolts arcing from cloud to cloud and down to the water's surface, a natural beacon that sailors have used for navigation for centuries. The exact cause is still debated, but it is believed to be a unique combination of factors. Warm, moist air blowing in from the Caribbean, forced upward by the surrounding mountains, combined with the methane gas rising from the vast marshes and oil deposits that enriches the atmosphere and helps to fuel the relentless electrical discharge. South America, therefore, offers us two profound and contrasting visions of a great lake. One, a sacred, freshwater sea held high in the sky, the cradle of ancient empires. The other, an ancient, oil-rich basin, now wedded to the ocean, perpetually illuminated by a storm that never seems to end. Our exploration of the world's Great Lakes has thus far focused on the living, on the immense bodies of water that define our modern landscapes. But the story of lakes is also a story of ghosts, of phantom waters that once dwarfed even the giants we know today. Lakes are not permanent features. They are ephemeral on a geological timescale, born from specific conditions and destined to eventually fill with sediment, dry up, or drain away. Their stories are written in the contours of the land itself, in the vast, flat plains that were once lake beds, and the fertile soils that are the legacy of their ancient life. To understand this epic cycle of creation and destruction, we must first travel back in time to the waning days of the last ice age in North America, to witness a body of water of almost unimaginable scale, Lake Agassiz. It was a temporary creation, a behemoth born from the death of the colossal Laurentide ice sheet. As this continent-sized glacier melted, it unleashed a deluge of fresh water. But the ice sheet, even in its retreat, still formed a monstrous dam to the north, blocking the water's natural drainage path toward the Arctic Ocean through what is now Hudson Bay. Trapped between the icy wall to the north and the rising land to the south, the meltwater pooled, creating a paleolake so vast it strains the imagination. At its greatest extent, around 13,000 years ago, Lake Agassiz covered an area of some 440,000 square kilometers, or 170,000 square miles. This was an inland sea larger than any lake on Earth today, larger even than the Caspian Sea. It submerged a vast swath of central North America, covering most of what is now Manitoba, as well as significant parts of Saskatchewan, Ontario, North Dakota, and Minnesota. Its waters were deep, cold, and forbidding, and its existence was a dynamic, violent affair. The lake was not a single, stable entity. As the ice dam to the north shifted, melted, and reformed, the lake's boundaries and outlets changed dramatically. At times, it drained south, carving the valley of the Minnesota River and pouring into the Mississippi River system. At other times, it found an eastern outlet, sending torrents of water into the basin of the Great Lakes. For over 5,000 years, this immense, shape-shifting body of water dominated the center of the continent. But its end, when it came, was cataclysmic. Around 8,200 years ago, the final ice dam holding the lake in place collapsed. In a geological instant, Lake Agassiz discharged its remaining contents into Hudson Bay and the North Atlantic Ocean. The scale of this final flood is difficult to comprehend. An estimated 163,000 cubic kilometers, or 39,000 cubic miles, of water, more than 7 times the volume of all the modern Great Lakes combined, surged into the ocean. This sudden, colossal influx of cold, fresh water was so significant that it disrupted the ocean circulation currents that regulate the planet's climate, triggering a brief but sharp global cooling event known as the 8.2 kiloyear event. Today, Lake Agassiz is gone, but its ghost remains. The vast, flat, and incredibly fertile farmland of the Red River Valley is its ancient lake bed, enriched by millennia of accumulated sediment. Great lakes like Lake Winnipeg, Lake Manitoba, and Lake of the Woods are its surviving puddles. mere remnants of a watery giant that once was. The story of Lake Agassiz is one of immense natural forces, a drama played out over millennia. But what happens when a great lake dies not on a geological timescale, but over the course of a single human lifetime? For this tragic lesson, we must travel to Central Asia, to the arid borderlands of Kazakhstan and Uzbekistan, to the place where the Aral Sea once shimmered in the desert sun. As recently as the mid-20th century, the Aral Sea was the fourth largest lake in the world, a vast, brachially watered expanse of 68,000 square kilometers, or 26,300 square miles. It was a thriving oasis in an otherwise harsh landscape, its waters teeming with fish that supported a commercial industry, employing tens of thousands of people. Bustling towns and canneries dotted its coastline, and fishing trawlers crisscrossed its surface. Its existence depended entirely on the lifeblood delivered by two great rivers, the Amu Darya and the Sir Darya, which rose in the distant mountains and flowed across the desert to replenish the water lost to evaporation. In the 1960s, however, the Soviet Union, in a monumental drive to achieve agricultural self-sufficiency, embarked on one of the most ambitious engineering projects in history. A decision was made to transform the arid plains of Central Asia into a vast plantation for water, thirsty crops, particularly cotton, which was dubbed white gold, and rice. To do this, the government constructed a sprawling network of canals to divert the waters of the Amu Darya and the Sir Darya, sacrificing the sea for the sake of the fields. The consequences were swift, predictable, and utterly catastrophic. Starved of its inflows, the Aral Sea began to die. The water level dropped, and the shoreline began to recede at an astonishing rate. By the 1980s, the retreat was no longer measured in meters, but in kilometers. Fishing boats that were once moored at the docks of towns like Moynak found themselves sitting on dry land, miles from the new shoreline. The water that remained grew progressively saltier. With its salinity tripling, the native freshwater fish died off, and the once mighty fishing industry collapsed entirely, leaving behind a legacy of unemployment, poverty, and social despair. By the year 2000, the Aral Sea had lost more than half its surface area and 3/4 of its volume. The single body of water fractured into two smaller, separate lakes, the North Aral Sea in Kazakhstan and the much larger South Aral Sea in Uzbekistan. But the disaster did not stop at the water's edge. The exposed lake bed, an area larger than the country of Switzerland, became a new man-made desert, the Aralkum. This new desert, however, was not made of simple sand. It was a toxic wasteland, a crust of salt and sand laced with decades of accumulated pesticides and fertilizers from agricultural runoff. The fierce winds that sweep across the region now pick up this contaminated dust and carry it for hundreds of kilometers, creating toxic dust storms that have led to soaring rates of respiratory illnesses, esophageal cancer, and other health problems among the local population. The disaster also profoundly altered the regional climate. The massive body of water had once acted as a moderating influence, buffering the region from extremes. Without it, summers became hotter and drier, and winters grew colder and longer, shortening the growing season and, ironically, damaging the very agricultural system for which the sea was sacrificed. In a small glimmer of hope, Kazakhstan built the Kokoral Dam in 2005 to isolate and save the smaller North Aral Sea. By concentrating the limited flow of the Sirdarya into this smaller basin, they have managed to raise its water level and reduce its salinity. And some fish have returned. But the vast South Aral Sea was left to its fate and has now all but vanished. A ghostly white salt pan visible from space. The story of the Aral Sea is the story of an ecological catastrophe on a planetary scale, a cautionary tale written in salt and dust, a stark and enduring monument to the devastating consequences of humanity's power to re-engineer the natural world. Our journey has been confined to a single, familiar world, a planet defined by the unique and life-giving properties of liquid water. But the universe is a vast and imaginative place, and the processes that shape planets are not unique to our own. The same forces of geology and climate that create lakes on Earth are at play on countless other worlds, under different suns, with entirely different chemistries. To find these alien shores, we must expand our very definition of what a lake can be and travel to one of the most mysterious and captivating destinations in our solar system. Our destination is the realm of the gas giants, specifically the majestic ringed planet, Saturn. And it is not the planet itself we seek, but its largest moon, a world shrouded in mystery, larger than the planet Mercury, named Titan. For centuries, Titan was little more than a point of light in astronomers' telescopes. When the Voyager 1 spacecraft flew past it in 1980, it sent back images not of a cratered rocky surface, but of a featureless, hazy orange ball. Titan was completely enshrouded in a thick, nitrogen-rich atmosphere, even denser than Earth's, and laced with a smog of organic compounds. This tantalizing veil hid the surface completely, but the data sent back by Voyager hinted at something extraordinary. The temperature and pressure conditions on Titan were close to the triple point of methane, a state where a substance can exist simultaneously as a solid, a liquid, and a gas. This raised the astonishing possibility that on this frigid, distant world, methane could play the same role that water plays on Earth, creating clouds, rain, rivers, and perhaps even lakes and seas. This tantalizing hypothesis remained just that for over 2 decades, a mystery locked beneath an impenetrable orange haze. Answering it required a new kind of explorer, a dedicated mission designed to peer beneath the veil. That explorer was the Cassini-Huygens mission, a joint project of NASA and the European Space Agency. After a journey of nearly 7 years, Cassini arrived at Saturn in 2004 and began a 13-year tour of the Saturnian system. One of its primary goals was to finally map the surface of Titan. To do this, Cassini was equipped with a powerful radar instrument, capable of sending radio waves through the thick atmosphere to bounce off the surface and create detailed images of the landscape below. In July of 2004, Cassini made its first close flyby of Titan, and the first radar images began to trickle back across more than 1 billion kilometers of space. What they revealed was breathtaking. The radar showed a complex and varied world of mountains made of water ice, vast dune fields of organic sand, and evidence of river channels carved into the landscape. But the most stunning features were vast, dark, and incredibly smooth patches concentrated near the moon's poles. These areas were so smooth that they absorbed the radar signal rather than scattering it back, a telltale sign of a liquid surface. The long-held theory was no longer a theory. Scientists were looking at lakes. These were not lakes of water. On Titan's surface, where the temperature hovers around a truly frigid minus 179 degrees Celsius, or minus 290 degrees Fahrenheit, water is as hard and inert as granite. The liquid that fills these basins is a cocktail of liquid hydrocarbons, primarily methane and ethane. Here, on this alien moon, a complete methane-based hydrological cycle is in action. Methane evaporates from the liquid surfaces, forms clouds in the thick nitrogen atmosphere, and then rains back down, a slow drizzle of liquid natural gas. This methane rain erodes the icy bedrock, carving intricate river networks and drainage channels that are hauntingly similar to those found in the deserts of Earth. These rivers then flow into the basins, collecting into pools, lakes, and vast seas. The sheer scale of these features is immense. The largest of these bodies, concentrated in the northern polar region, are true seas. There is Kraken Mare, the largest, a sprawling sea of liquid hydrocarbons larger than Earth's Caspian Sea. There is Legia Mare, the second largest, a sea so deep and so pure in its methane composition that its floor is almost perfectly transparent to Cassini's radar. And there is Punga Mare, the third great sea. Dozens of smaller, named lakes, many nestled in steep-sided, canyon-like depressions that appear to have been carved out by the liquid, dot the polar landscapes. In a nod to our home world, one of the first confirmed lakes in the southern hemisphere was named Ontario Lacus, for its similar size and shape to North America's Lake Ontario. The ultimate confirmation of this hydrocarbon world came on January 14th, 2005, in one of the most daring and dramatic moments of space exploration. The European Space Agency's Huygens probe, which had piggybacked with Cassini across the solar system, detached and began its descent through Titan's atmosphere. For 2.5 hours, it parachuted through the orange haze, snapping pictures of the world below. The images it sent back were astonishing, showing a landscape of branching, dendritic channels that looked for all the world like a river system on Earth, flowing from a high plateau down to a darker, flatter region. It was incontrovertible proof of liquid flowing across the moon's surface. The probe's landing was equally revealing. It touched down not with a splash, but with a gentle thud, in a place that scientists described as being like damp sand. It had landed on the shoreline or floodplain of a methane lake, a place saturated with liquid hydrocarbons. For a brief time, this small, robotic emissary from Earth sat on the shores of an alien sea, sending back the first and only images from the surface of a world in the outer solar system. Even after this groundbreaking discovery, Titan continued to surprise. Later in its mission, Cassini's radar spotted something strange in Ligea Mare, a feature that appeared in one radar pass, only to vanish in the next. Then it reappeared. Scientists dubbed these transient phenomena magic islands. Their exact nature is still a mystery, but the leading theories suggest they are either large bubbles of nitrogen gas fizzing up from the seafloor, or perhaps floating, iceberg-like clumps of organic solids. Whatever they are, their existence proves that the lakes and seas of Titan are not static, but dynamic, changing environments with their own form of weather and geology. While Titan is the only world in our solar system known to have stable bodies of surface liquid today, the search for extraterrestrial lakes extends elsewhere. On Mars, our robotic rovers have sent back overwhelming evidence that the red planet was once a much warmer and wetter world. In places like Jezero Crater, the landing site of the Perseverance rover, we see the unmistakable remnants of a river delta that flowed into a vast, ancient lake billions of years ago. The story of Mars is the story of a world that lost its water. Its lakes long since evaporated into a thin, cold atmosphere. The discovery of lakes on Titan and the evidence for ancient lakes on Mars has fundamentally expanded our understanding of the universe. It shows that the processes that create these beautiful and vital features are not unique to Earth. The existence of a liquid medium, a solvent, is a critical ingredient for life as we know it. And finding liquid on another world, even if it is a liquid as alien as methane, electrifies the search for life beyond Earth. It forces us to wonder what strange form of life might be able to arise in the frigid hydrocarbon depths of Kraken Mare, a question that for now remains unanswered. The concept of a lake has been untethered from water and from Earth, transformed into a universal phenomenon. a potential oasis for life, waiting to be discovered among the countless worlds that populate the cosmos. Our journey to the hydrocarbon seas of Titan has shown us that the idea of a lake is a universal concept, a consequence of physics and chemistry playing out across the cosmos. But now we return to Earth, to the familiar world of liquid water, to understand a more profound truth, that our planet's lakes are far more than mere geographical features. They are not passive basins filled with water. They are dynamic, beating hearts at the center of vast ecosystems. They are the lifeblood of the landscapes they inhabit, powerful engines that regulate climate, sustain biodiversity, and act as critical hubs in the planet's great circulatory system. Their influence extends far beyond their shores, shaping the lives of every plant and animal for hundreds of kilometers around them, including our own. The most fundamental role of any lake is its position as a central reservoir in the hydrological cycle. A lake is a point of pause and reflection in the relentless journey of water. It gathers moisture from every available source, rain falling directly on its surface, runoff from the surrounding land, water flowing in from countless streams and rivers, and the slow, unseen seepage of groundwater from below. In this, a lake acts as a great capacitor, storing water during times of plenty. This stored water provides a steady, reliable supply to outflowing rivers, keeping them flowing even during prolonged dry spells, and sustaining the life that depends on them downstream. By absorbing the sudden deluges of great storms, large lakes also act as natural flood control systems, their broad surfaces absorbing and distributing the impact of a surge that might otherwise cause catastrophic flooding in river valleys below. But a lake is not just a place of storage. It is also a place of release. Its vast surface is a platform for evaporation, sending immense quantities of water vapor back into the atmosphere. The Great Lakes of North America, for instance, release so much moisture that they significantly influence the continent's weather patterns, contributing to the humidity and rainfall far to the east. This influence on the atmosphere is the key to another of a lake's great powers, its role as a climate moderator. Water has a very high specific heat capacity, meaning it takes a great deal of energy to raise its temperature, and it releases that energy very slowly as it cools. Land, by contrast, heats up and cools down quickly. A large, deep lake acts as a colossal thermal battery for its entire region. In the spring and summer, as the sun beats down, the lake absorbs a tremendous amount of solar energy, its cool waters keeping the surrounding land from becoming excessively hot. The cooling onshore breezes that offer relief on a sweltering summer day are a direct gift from the lake. Then, as autumn and winter approach, the lake begins to release this vast reservoir of stored heat. It gives back the warmth of the summer sun to the cooling air, making the winters along its shores significantly milder and longer than they would be just a few dozen kilometers inland. This effect is so pronounced that it creates entire agricultural regions, like the fruit belts along the shores of Lake Michigan, where the lake's moderating influence protects sensitive crops from the killing frosts of early spring and late autumn. This same process can also unleash one of nature's most formidable displays of weather: lake effect snow. When frigid, dry Arctic air in the winter blows across the relatively warm, unfrozen surface of a great lake, it picks up both heat and a tremendous amount of moisture. As this now laden air reaches the colder land on the downwind shore, it is forced to rise, cool, and dump its moisture as staggering quantities of snow. In the snowbelt regions of North America's Great Lakes, this process can deposit several meters, or more than a dozen feet, of snow in a single season, creating a unique and challenging climate entirely of the lake's own making. Beneath the surface, a lake is a complex, three-dimensional world, a vertically structured environment that changes dramatically with depth. In temperate regions, lakes undergo a remarkable annual dance of stratification. In the summer, the sun's energy heats the top layer of water, creating a warm, sunlit, and oxygen-rich zone called the epilimnion. This is where most life, from microscopic phytoplankton to the fish that feed on them, thrives. Far below lies the hypolimnion, a realm of cold, dark, and still water, cut off from the sun and the atmosphere. Separating these two layers is the thermocline, a narrow band of water where the temperature plummets rapidly. As autumn arrives and the surface water cools, it becomes denser and begins to sink. Eventually, the entire lake reaches a uniform temperature, and the winds that sweep across its surface are able to mix the water from top to bottom. This event, known as the fall turnover, is the lake taking a deep breath. It brings oxygen-rich water from the surface down to the depths and pulls the nutrient-rich water from the decaying matter on the bottom back up to the surface. A similar turnover happens in the spring after the ice melts. This seasonal mixing is the engine of the lake's productivity, a vital process that recharges the ecosystem and fuels the explosion of life each spring. The absence of this mixing, as seen in permanently stratified lakes like Tanganyika, creates a two-tiered world: a thin layer of life on top, and a vast, lifeless, anoxic abyss below. This structured environment is what allows lakes to become such incredible hotspots of biodiversity. They are not uniform pools, but mosaics of different habitats. The shallow, sunlit waters near the shore, the littoral zone, are the lake's nursery, where reeds and water lilies provide shelter for young fish, amphibians, and countless invertebrates. The open, sunlit water of the limnetic zone is the domain of plankton and the larger fish that hunt them. And the dark, deep profundal zone is home to specialized creatures adapted to a world of cold, pressure, and low oxygen. When a lake is ancient and isolated, like Baikal or the African Great Lakes, these zones become evolutionary laboratories. Trapped within the confines of the lake for millions of years, populations of organisms can diverge and specialize, adapting to fill every available niche, resulting in the spectacular explosions of endemic species that are found nowhere else on Earth. These lakes become living museums of evolution, offering us an unparalleled window into the processes that create the diversity of life itself. A lake's influence is not contained by its shores. It is the center of a web that extends far into the terrestrial world. It is a watering hole for deer and moose, a hunting ground for eagles and ospreys, a breeding site for dragonflies, and a crucial stopover for millions of migratory birds on their epic intercontinental journeys. The health of a lake is therefore a direct reflection of the health of its entire watershed. It is an honest accountant, a final repository for everything that happens on the land that surrounds it. Lakes are the lifeblood of ecosystems because they are active participants, not just passive settings. They breathe, they regulate, they moderate, and they create, making them some of the most vital and precious natural systems on our planet. Our journey through the world's Great Lakes has taken us across continents and to the very edge of our solar system. A voyage that has stretched from the familiar shores of fresh water to the alien coastlines of liquid methane. We have stood on the banks of paradoxical giants like the Caspian Sea, a trapped remnant of an ancient ocean that is legally and geologically a world unto itself. We have navigated the immense freshwater seas of North America, colossal basins carved from the bedrock by the slow grinding of continental ice, which became the arteries of an industrial revolution. In the remote depths of Siberia, we have peered into the abyss of Lake Baikal, the planet's oldest and deepest lake, a living museum of evolution where the water holds the memory of millions of years. We have traveled the length of Africa's Great Rift Valley, witnessing the shallow immensity of Lake Victoria, the profound, ancient depths of Lake Tanganyika, and the explosive biodiversity of Lake Malawi, a story of life's incredible power to adapt and diversify. We have ascended to the high Andes to behold the sacred sky-blue waters of Lake Titicaca, the cradle of empires, and descended to the shores of Lake Maracaibo, an oil-rich basin perpetually lit by a silent, electrical storm. Yet, we have also seen their ghosts. We have traced the faint shorelines of the vanished Lake Agassiz, a glacial giant whose death reshaped a continent and altered the global climate. And we have witnessed the modern tragedy of the Aral Sea, a monument to how quickly a great water can be turned to toxic dust by human hands. Finally, on the frigid, hazy moon of Titan. Our very understanding of a lake has been untethered from water itself, expanded to include seas of hydrocarbons beneath an orange sky. From this grand tour, we return with a deeper truth, that a lake is far more than its simple definition. It is a climate regulator, an engine of biodiversity, a sacred place, a historical archive, and a vital resource. They are the quiet heart of our world's landscapes, mirrors to the sky that reflect not just the clouds above, but the long, complex, and fragile story of our planet.